Hi, today we're going to go over lesson 4.7 optimization problems. This lesson is essentially using our previous knowledge on how to find an absolute extrema on a specific interval and apply this to solving word problems. And these word problems are almost always to maximize or minimize a certain value, such as an area, a surface area, a volume, depending on the equation. So it's important to think of it like this. Let's say we have this graph here, y equals 9 minus x squared, and that will look something like this. And let's say the interval is -3 to +3, and that's our interval. And if we want to find the maximum, we have to set the derivative equal to 0. So the derivative of this equation here is -2x, and if you set that equal to 0, we can get x is equal to 0. And when x equals to 0, which is the maximum here, you can see y is equal to 9. Now, in order to make sure that this is a maximum, we have to test our endpoints. And our endpoints, if x is equal to positive or -3, then we get y is equal to 0. So we can see that x is equal to 0 is our maximum because it spits out our biggest value, which is y equals 9. Now, what if this graph here represented the area of, let's say, a rectangle in relation to the length of its sides? Now, at its maximum, this is the largest the rectangle can be on its constraint, which is -3 to 3. And that's exactly what we're trying to find in our optimization problems. So let's start off with a really simple example to explain how this process works. So let's say a Coca-Cola can needs to hold 1,000 centimeters cubed of liquid, minimize the materials needed. Now our first step and most important step is to draw. Drawing is really important when it comes to solving a word problem, I found in my experience, because it allows you to visualize what you're trying to solve and makes it easier to come up with the equations that you need. Now, this is our Coca-Cola can. And our second step is to figure out what we're trying to minimize or what we're trying to maximize. So we're trying to figure out the equation that we need to find the minimum or the maximum on. And so you can see here in the wording, minimize the materials needed. So we have to find the minimum on the surface area equation. So our surface area equation is equal to 2 pi r squared plus 2 pi RH. Our second step is to find the constraint. So this is the interval that we're trying to find. Now, the constraint you can see here is that it has to hold 1,000 centimeters cubed of liquid. So our volume has to equal 1,000 centimeters cubed. So our volume equation is pi r squared h, and if we set that equal to 1,000, now we have to solve for one of our numbers here, and so the easiest one to solve for is h. So h is equal to 1,000 all over pi r squared. Now we have to plug this into the original equation because we have to apply our constraint to our graph. So if we solve this, we can get 2 pi r squared plus 2 pi r, 1,000 all over pi r squared. And if we're going to simplify this, we can get 2 pi r squared plus 2,000 r to the -1. And if we're trying to find our critical numbers, once again, as you saw above, we have to set the derivative of this equation equal to 0. So real quick, I'm going to derive this equation, and we can get 4 pi r minus 2,000 r squared. And if we set this equal to 0, we get r is equal to cube root of 500 over pi. That is our critical number. Our r is cube root of 500 over pi is our critical number. And if we plug that into a calculator, we get r is about 5.42, and the height is about 10.84. Now, when we figure out the height, we plug our r value into the original equation here. Our last step is to test our endpoints. But since we don't have endpoints, we have to find another way to make sure that this is the minimum on our graph. Because of the way our constraint is set up, we don't have specific endpoints. So one of the ways to test is the double derivative test. And a lot of students make the mistake of not testing these endpoints or not using this test, and sometimes this critical number here isn't the minimum or isn't the maximum. So it's very important to test to make sure that it is the answer that you want. So our double derivative of our surface area equation is equal to 4 pi plus 4,000 all over r cubed. And for the double derivative test, we have to find out if this graph is concave up or concave down. And if we plug our critical number into this equation, we get two positives, meaning that our double derivative is greater than 0. And this expresses that our graph looks like this. It's concave up, which means that it does have a minimum right here. Another way to test this to make sure it's a minimum is that our r value, we can use the single derivative test to make sure that the graph is going down on the left and up on the right. So on the left, we can pick a value of 5, and on the right, we can pick a value of 6. So if we plug 5 and 6 into our first derivative, we can get a negative on the left and a positive on the right. And this means that our graph is going down on the left and up on the right. And these two tests can conclude that r is about 5.42 is our minimum. So finally, we have to write a conclusion sentence. This is really important. Please don't forget this step. So the materials needed are minimized when the radius is 5.42 centimeters. Please don't forget the units. That's very important. And the height is 10.84 centimeters. And the surface area is 553.73 centimeters squared. Area is always squared, don't forget that. So that is our answer right there. Hopefully my instruction helped you, and hopefully you understand this entire lesson. Thank you for watching.